Okay, so yeah, recording has started. Good. So today we are going to look at, as I said in the last lecture, today we are going to look at the shortest path problem in a graph. Okay? Shortest. We have looked at it before also. So let's take G to be a graph. The directed graph, to be precise. And for each edge in the graph, we have Cij, right? Which is the cost of going from I to J. Okay. And here this cost is basically we want it to be any real number. And we had seen that earlier we had seen Dijkstra's algorithm, and where the costs were positive costs. Right. So here what do we have? We have that the cost can be anything. Right? So what happens when the costs can be negative? Right. And this cost being negative can be useful in many scenarios, can be useful in modeling. In like you have a graph of currencies where if you exchange some currencies, how much you gain, or how much you lose. So you can have negative, you can have positive if some currency exchange happens in some direction and so on. And then you can have negative costs there, depending on whether you are losing money or gaining money by going from this currency to that currency and so on. Right. Okay. So now we'll be considering two problems here. Okay. So first is given a graph with edge weights, decide if, so let's say the graph G, decide if G contains a directed cycle of negative cost. So what is this total cost? It's so suppose the directed cycle is C. So do you want to ask, does there exist C such that summation of Ij belonging to C, Cij is less than 0? So this is one question we'll be addressing. And the second question is the shortest path question, is if the graph has no such thing, has no negative cycle, right? Then find for given, let's say, S and T, find a path P from S to T of minimum cost. Okay? That is minimizes summation ij belongs to P Cij. So are the problems clear? So this is called the shortest path problem or minimum cost path problem. And why we want to detect such things like these negative weight cycles and so on, because they might be useful in again, as I said, modeling that now you have these things like, as I said, suppose currency exchange. So you want to know whether you can start from some currency like suppose INR and exchange the currencies and come back to INR and totally like in total make a profit. So suppose profit is negative and loss is positive because it's the cost, and you want to start from some currency. So you want to detect such cycles which are there, which can you can just make a circle and without doing anything you make some money. Okay. So in that thing they might be useful. Imply like some way of making profit. Now also, why do we need this requirement for the second part? That if the graph has no negative cycle, why do we want it here in the second part?
So because if there was a negative cycle, then we could get very low cost, as low as we wanted.
Yeah. So because then we could go around the cycle, a negative cost cycle, as many times as we wanted, and get the cost arbitrarily low. Right. So that's why it makes sense to have that requirement for the shortest path. Okay. Good. So let's just see that, okay, for this problem, why I mean I had asked in the exam also this that why Dijkstra doesn't work for negative weights, but let's just see why it doesn't, like with a quick example. So suppose the edge weights were like 2, 3, 1, and let's say -6. Right. So let's say this was S U V W. So Dijkstra would just look at this because this is the lowest cost edge coming out of S, and put the distance of S comma V to be 2, sorry, 1. This is what it will do. But actually the shortest minimum cost path is this, where it goes, and actually distance of S comma V is -1, and this is the shortest path, which Dijkstra won't be able to see. Another way one can approach this is that, okay, what if we increase the weights by some constant, like basically all the weights, such that all the weights are positive, and then use Dijkstra's. How does it go away? Okay. Then use the extras, right? So how can we do that? I mean, does that work, or any guesses whether that works or not?
No, sir, it will not work because SV will increase by W, and if you take SUWB path, then it will increase the weight to 3 times W.
Yeah. So actually, it does not work. So there are some counter examples, simple ones. So like again, like the book gives this example that this is 2, 2. Let's say now 3 minus 3 and 3, and this is S and this is T. So here, what is the minimum weight? What is the cost of minimum cost path? It has value 3, right? And this is the path. Suppose the edges were like directly in this direction. And now if you increase, let's say by 4, all the edge weights. So what does the graph become? It becomes 6, 6, 7, 1, 7, right? And what is now the minimum weight path? It is this one of weight 12. And the path changed. So you did not preserve the structure of the problem, right? So this approach also does not work, right? So what do we do now? So again, let's go to dynamic programming that we have been doing for quite some time now. Okay. So this dynamic programming algorithm was created by the one that we are going to see is called Bellman-Ford algorithm, and this was created in like early 70s, I think, or something, or if not earlier. And this is one of the first dynamic programming algorithms that is known. And then Bellman was the one who started this whole thing basically of dynamic programming and how to do it. So how do we start? So again, so do we want to do the same thing like we were doing earlier, that okay, what will opt I represent? Opt I is uh, shortest path between S and T using first I vertices, or something like this. Suppose we want to do, right? But it turns out that this itself will not be enough, because then you don't really know how to do this. So instead of going through the wrong thing again and marking, let's go to the what is the clear thing, what is the right thing. And for that there is an observation or a lemma, you can say, which will be useful. So this one is almost there, but not really. This will not help us much. Okay, uh, so to get the structure, let's first look at that. What does the negative cycle imply, right? So it says that if G has no negative cycle, then the shortest path from S to T uh, let's say this way, then there is a shortest length path from S to T that is simple. And what do you mean by simple? Does not repeat any vertices. and hence has length. How much its length can be? If a path does not repeat vertices, then how many vertices it can have?
Less than equals to n minus 1.
Sandak, I'm not able to hear you. Say again.
At most n minus 1.
At most n minus 1 edges, so has length, and at most n minus 1. Right? Okay. Number of vertices can be n, and the number of edges can be at most n minus 1. And what is the proof of this? Anyone quickly? What happens if vertices get repeated?
Since there are no negative cycles, we can remove all the edges between the cycle and we'll get a path with lesser cost.
Exactly. So suppose you have a path which repeats some vertex. So suppose this vertex gets repeated. That means there is, a path from it to itself, which is a subpath of the original path. And then you go ahead like this. So now this cycle has non-negative weight. So you remove it and the total path remove it from the path. Cost can't go up. Right? So that is the proof of this. I mean, I'm not writing the whole thing, but you get the idea. Okay? Good. So this gives us an idea of the subproblem that, okay, now we know that n minus 1 is the highest length or the maximum length path. Then why don't we, the subproblem, we put it on the length of the path, right? So subproblems are going to be of the form, let's say, opt of I comma v, right? So minimum cost of a VT path having at most I edges, right? So this is our subproblem that, from we have to get to T, and for every V in the graph, so this for all V in V, and for all I belonging to 1 to n minus 1, we define this subproblem. And for every V, we find out that, okay, if the path length is I, then what is the minimum length path? What is the cost of the minimum length path? Right? So what is going to be the final solution in terms of these subproblems? What is the optimum cost?
So optimum of n minus 1 comma s.
Of n minus 1 comma s. Why? This is the because the path length of shortest path we have already shown by the lemma is less than n minus 1. So at most n minus 1 edges, and then this is the minimum cost of a ST path having at most n minus 1 edges. So that is the minimum cost of an ST path due to this lemma. Right? Any questions till now? Okay, if not, then just like now, let's try to express opt now I comma v as smaller subproblems. Okay, and like so this is again like like in this thing segmented least squares thing, we had many choices to choose from. There was not just one, and so this is again an example of multi-way choices. Like segmented least squares. And what do I mean by that? So let's now look at it, right? That how do we break it into the problem? So let P be a path corresponding to opt IV, right? That is how we start. That let this be your optimum solution, this be a thing. So let P be a path which corresponds to opt I comma V, right? So now there is this V. From V you go to T, right? And now you want to write this in terms of smaller subproblems. So this is your P, which corresponds to. So now there are these two cases. The first case is that if P itself has shorter length. If P has less than I edges, then what can we say? Which smaller subproblem we can write this as?
I minus 1 comma V.
I minus 1 comma V. Why? Because the path P now has less than I edges. So basically it has at most I minus 1 edges, and then opt of I minus 1 comma V will record the minimum cost of a VT path of length at most I minus 1, right? So that is already stored in that case. Okay, so that is good. So this is case 1. Now case 2, if P has exactly I edges, right? Then the path has to go from V to some W. Let W be the first vertex after V on P, right? So suppose we know this W. Suppose we know this. That which one is this W? Then can we write a recurrence? I mean, yeah. Then can we write what it is?
Cost of V comma W plus opt of I minus 1 comma W.
Right? Because now this is a path of length I minus 1, of cost of length at most I minus 1 from W to T. So that has already been stored in W, I minus 1 W. And then you add this cost to that, the cost of going from V to W to that, right? Any question about these two? Okay, so now these are the two cases. So now we are ready to get the recurrence, right? So for I greater than 0, what is the recurrence that we get? Opt I comma V is equal to minimum of opt I minus 1 comma V. And what is going to be the second quantity? Here we assume that we know this W. but we don't know that W.
We can take all the outgoing edges from V and all those adjacent vertices. And
Yeah. So let's just say minimum over W for now belong to V. C VW plus opt of I minus 1 W. Minimum over this whole quantity. Right. Is this clear? Any questions?
Excuse me, sir.
Yeah.
So can we say that CVV is 0?
CVV is 0. Yeah, I mean, we can say
So
0.
like we can kind of include the first term in minimum in the second only, like when W is equal to V,
Sorry.
uh, when we consider W equals to V, so it would become CVV plus opt of I minus 1V.
Yeah, I mean, yeah, you can do that as well. That is fine. But then, like, do you assume that there is an edge from a vertex to itself or not?
Yeah,
Yeah, so that is why I'm just putting I greater than 0, just to, like, just so that things are clearer, that we are considering simple paths which are not from a vertex to itself and so on. Yeah, I mean, but you can do such things, of course.
yeah.
You yeah. Good. Good. So now we have the recurrence, and now we can write the algorithm. And so the recurrence, I hope, is clear. And so the algorithm will have a two-dimensional array. So should I start here? Okay, let me start here. So shortest path, and then you are given G, you are given S, you are given T. These are the input, and let N is equal to, let's write N is equal to number of vertices in G, right? And now you define an array, a two-dimensional array, M, which is like 0, 1, 2, to n minus 1, that is the first index, and then v1, v2 to vn, that is the second index, right? And now define, just initialize things. M of 0 comma t is equal to 0, and m of 0 comma v is equal to infinity, because 0 comma t is like, 0 length paths from t to t is 0. So that's what we are saying here. That is the initialization that Sean also talked about. And m of 0 comma v is infinity for all v belongs to v such that v not equal to t. So this is just the initialization, and that's it. Now for I is equal to 1 to n minus 1, this is the path length. And for v belonging to v in any order, basically, you can go in like, that order also if you want, any order. Then compute MIV using the recurrence, and this for, and then return what we wanted, right? M n minus 1 comma s, right? So this is the algorithm. So what does it say? Algorithm says that, okay, first pick the path length, and then update the values of, that, okay, what is the minimum cost path of length I starting from, 1 to n minus 1. So how can we get to t using at most I edges? and then update those values, and then using those values, update the values for higher values of I, right? And that uses this recurrence that we have come up with. This one. So any questions about the algorithm, what the algorithm is doing? Is there? No? Okay. So again, like it's a two-dimensional, like, sort of array. On one side you have path length 0 to n minus 1. To the other side you have v1 to vn. And then first you fill up this, basically this column, then you fill up this column, then you fill up this column, and so on. And finally, wherever your s is, and this n minus 1, this is going to be your final answer. Okay, so if no questions, let's just quickly do an analysis. And what does the analysis do? It, like, it has to go for correctness. I'm not going to show the correctness. It will follow by induction on what? Induction on what? And the recurrence. What should be the induction on for the correctness? Somebody.
Find those links.
Yes, on I. And then the running time analysis, size of table, order n square, because n minus 1 here and there. And for each entry, how much time we take? Order n at most, let's say. And so total time is at most order n cube, right? But again, let's just quickly, like, improve the running time analysis. And I think somebody had suggested that while suggesting the recurrence itself. So suppose the graph has m edges and m is less than n square. It's much smaller than n square, right? Then we can, then we can save something. And how? So let's look at the recurrence again. Copy it down. So this is our recurrence. And so how can we? So somebody suggested that this we need to do only for W such that VW is an edge. Right? So that means how for each V, so to compute I comma V, M I comma V, right? For each v, how many things we need to consider?
The outgoing degree.
We need to consider, let's say, d plus v, right? Where d plus v is the outgoing degree. Is basically whatever size of the set such that VW such that, yeah, I mean, such that VW is an edge. Okay, so this is what it is, and so now how does that give us a better analysis? That now for each I, and how many I's are there, right? So number of, how many different length paths are there? I's, right? Is n minus 1, right? And for each I, for each V, we take d plus of V time, right? So total time is, let's say total time taken by the algorithm now. Is order of n times summation over all v, because for each v we take for each I we take this much time, d plus of v, right? For each I, for each v we take this much time, so for each I is this n, and then for each v we take this much time, and this is it. And this is what is this number?
M.
M, exactly, right? Why? Because now you are counting all the edges, and every edge is counted exactly once here because it is outgoing for one vertex. So there is no double counting happening. That happens in the case of undirected graphs. So every edge is getting counted exactly once for the vertex where it is coming out from. And that's why you get an n times m algorithm, which is better than order n cube if m is very small as compared to n square. Any questions about this? Okay. And also let's do some improved space or memory requirements. Yeah, is it on? So how do we improve the memory requirements? So currently the table has size order n square. And again, if we want to like just compute the opt, then of course, we can do in order n, because like previously, we just need to maintain that column or that row, like, the I minus 1th, and the next one will follow. So that is not going to be very hard. But how to get suppose we don't want to just compute, but we also want to get the path also. Then what can we do?
So save the element which comes next in the path to till t.
Exactly. So in that case, for each v, keep the node that comes next. So first, don't keep this thing anywhere. Don't keep m I comma v. Just keep m of v. Okay, and keep the node that comes next on a path of cost mv. Right?
Sir, sir,
Yeah,
if we only keep MV, then how are we updating simultaneously?
yeah,
Because
yeah.
if
I'm just going to tell. Just wait for a moment. Okay. So what does it mean by MV? So MV, I do minimum over again MV, the previous value, comma minimum over W belongs to V. Again, like your W only outgoing edges from V, you can do C of VW plus M of W. And you just do this n minus 1 times. Yeah, Amit,
sir,
now your
yeah,
question.
sir, in this only, let's say that we have performed first iteration for right now, and
Yes,
MV is that path, shortest path till one edges, using at most one edges.
yes,
Sir,
correct.
next, when we want to update it for the second iteration, I'm saying
Yes,
if we update it node by node, then we are updating some paths so that it is at most two edges while others remain at most one edges.
yes, yes. But after, so here also, I mean, even in this algorithm, you are going from for some vertices, and then you do among the vertices one by one, right? So some
Yes,
paths
sir.
remain. Yeah.
Sir, but in this case, mi minus 1 is always the same. Mi minus 1 comma
Here
v.
also, mi minus one will always be the same. So all I'm saying is that after you have completed the I iterations, value of mv. So let's write it as a lemma. Okay. So you can show this that throughout the algorithm. So now the algorithm remains the same. Here, instead of the recurrence, instead of MIV, you just write MV here, right? And you use the new recurrence to update this. And what you can show is that throughout the algorithm,
Sir, in the above recurrence, in the old recurrence, can you scroll up a little?
yeah, it was here also, I guess, where we had it here. Yeah.
Yes, sir. Sir, here opt I comma v is equal to minimum of opt I minus 1 comma v, comma
Yes.
minimum of c v comma w plus opt of I minus 1 comma w.
Yes.
Sir, I'm saying if we have updated MV, that means it will change to opt of I comma v is equal to minimum of opt I minus 1 comma v,
Yes.
but then it will be comma minimum of c v comma w plus opt of I comma w, because we could have changed maybe w at some point.
We could have changed W at some point. Yeah, yeah. So if you have changed W at some point, then you can. So you're saying that we can now use that path to get to. That is also fine. That now we are in the ith iteration. You are saying that we might have changed things to I plus one,
Other nodes. Yes, sir, exactly.
but that's the only problem, right? It cannot jump more than that.
Yes, sir.
Right? So, but that is still fine because finally you want the minimum length path, and you are changing the value of
Okay,
MV only if you have found a smaller length path,
okay, sir.
right? So now we are not keeping the I. So that thing, of course, it will slightly deviate from what we were doing earlier. But still, always whenever we store an MV, whenever you store a path, length of path MV, then that still means that that is the minimum length path you have found till now.
Okay, sir.
Okay, and then you will keep updating it, and then finally when your I reaches n, then you know that okay, now whatever possible paths that I could have found, I have found. Okay.
Okay, sir.
Yeah, good. Yeah, so MV will be the length of the shortest path. From V to T discovered till that iteration. Of length, let's say I or maybe I plus 1 of length. And this ordering can be, something else or Joby. And that is still fine because you will keep discovering the new paths, and then you can finally output after n minus 1 iterations. You can stop. So this you can show, like again by induction. And the memory now requirements is order n, right? For this. But still here we are just updating the MV, which is just the value of the path. But again, now we store, what do we store? That again, we store the next of V, or they call it first of V in the book. Next vertex after V in the path of cost and V. And how do we update this? So whenever we update this MV using this value, whenever let's say it is less. So we update MV only when this one is less, let's say, because we might want to update when it's like, equal also, but let's not do that. Let's update MV only if this value is less than the current MV. So if this is less than MV, then we update it. Update this to this value, MV to this value, and then also update first of V to be W. Okay. So next vertex after V, and this gets updated when MV gets updated. Okay. And now using this, now we want to show that, okay, like, the we can trace the shortest path, right? So we can define a graph on these edges. Let P be a graph on vertex set V and edge set these vertices V comma first of V. Okay. So let P be a graph, which is just like, you take all the vertices and you take all the edges which go. And what you can show first will be a lemma which will show that if there is a negative cycle, because we wanted to find negative cycles also, if there is a negative cycle, or let's say the other way around, if there is a cycle in C, in P, it must have negative cost. And this is not that hard to show. So let C is equal to V1 to Vk and then V1. Let this be the cycle. And let Vk, V1 be the last edge to be added to P. And what does that mean? That we put first of Vk to be V1. Right? So now, how do we update these things by definition? That these are the V comma first of V. So then we have M of Vi is greater than or equal to C of Vi plus 1 plus M of Vi plus 1. Right? And so this we have for all I in K minus 1. And then for the final one, M of Vk is strictly greater than C of Vk V1 plus M of V1, right? So this is what we get by the equations because these edges are added to the cycle. That means the first values have been changed, and the first values change only when the MV gets updated, and MV gets updated when this happens, when this value is less than this value, right? And then you just sum them up, all of them up. So these values get cancelled, MVI and MVK, because MV1 and MVIs are here. So all these get cancelled, and what you get is 0 is greater than CVI, VI plus 1 plus CVK, V1, which is the cost of the cycle, right? So this you can show that this happens, that the negative cycle is there and that can be detected. And then you can show another lemma that if there is no negative cycle, then the shortest path in G from S to T is the path in P, is the path from S to T in P. Okay. And this again, like, so the proof is like just 2 lines. Let me just complete it. I'm over time, but let me just so let V is in V and W is equal to first of V. Okay, so V to T, not S to T. Is the path from V to T in P. Okay, so let W is equal to first of V. Now what do we have? That M of V is equal to CUW plus M of W. We know that. And then we keep expanding it. Now M of W is whatever is the CWX plus M of X and so on till we finally reach M of T, right? And M of T is equal to 0. So what is this whole length? So M of V is equal to C of UW plus C of WX plus whatever, right? Like this. And this is the length of the path in P. And this is the shortest length path from V to T. So shortest length path from V to T is length of the path from P, in P, from V to T in P. And that is what we wanted to show. So why this lemma was necessary? Why are we showing this lemma? So that now we show that following this graph P, following the path in graph P, we will get the shortest path from any vertex B to T. And in particular, we can get from S to T. Okay. But there is a caveat there that the graph should not have any negative cycle. So if there is a negative cycle, then there is a cycle in this P. Any questions? So basically you start from this V and you just go like, and if you reach V or any vertex gets repeated, then you just output that there is a negative cycle, and otherwise you will reach T. So any questions about the algorithm and this improved versions? So algorithm is simple. The improved versions are like slightly you have to think a little bit more carefully, but I think you can figure it out. Any question? Okay, so if not, then we'll finish. Yeah, we are quite a bit over time, so we'll finish today and see you guys tomorrow. Thank you for coming.